Brent Sherwood was educated at Yale and the University of Maryland. He has advanced degrees in architecture as well as aerospace engineering. He is an associate fellow of the American Institute of Aeronautics and Astronautics, where he chaired the space architecture technical community, the only one of its kind worldwide until 2020. In this year, he was also awarded the Columbia Medal by the American Society of Civil Engineering. Brent Sherwood has made space architecture his life's work in education, career, mentoring, and he has published over 50 papers on the exploration, development, and settlement of space, including the book Out of This World, the new field of space architecture. Together with a few other pioneers in this field, he has worked on promoting and also professionalizing the field space architecture. Today, as academic director of our new MBA Space Architecture at TU Wien, I am delighted to let you know that Brent Sherwood has agreed to be part of our faculty team. We are all excited, and it's time to hand over the micro to space architect and visionary Brent Sherwood. Welcome.
Thanks so much, Sandra. Good evening, everybody, or whatever time it is where you are. And thanks for being here. My purpose today is to talk about the future of human spaceflight in some ways that are not so common. And you'll see I've titled it Four Futures. Really, the takeaway that I'd like you to remember is that what we build and what we do in space is up to us. We have choices, and those choices will determine what we invest in. What we invest in will determine what we're able to accomplish. And in fact, those choices will govern the speed and the extent of our development of space for humans. You'll see why that's important in a little bit. But it's quite critical to recognize that choice is part of what we do as consumers of the space culture, as funders of space work, and as citizens of the world. So the way I view the future of spaceflight is about what it means to expand the world that we live in and experience. I was born in 1958, the same year as NASA, and I grew up in the 60s and 70s. And for me, it was always obvious that what you're seeing here would be our future in space. Moon bases and space hotels and cities on Mars and so forth. And it turns out that those things are very hard, very expensive, much more complex politically, geopolitically, financially, and technically than anybody really imagined in the 50s and 60s. But we are getting closer. The way we view it at Blue Origin is that we live on a planet which is vast, but the habitable part of that planet is actually very small. It's this very thin skin around the planet which is capable of supporting the biosphere. So just a few kilometers of atmosphere, a couple of kilometers of ocean in some places, and that's it. It's an onion thin skin around this giant planet. And so that poses limits to how large we can grow as a species, and particularly how extensive our development of resources can be in that thin biosphere. So we call those the Malthusian limits, right? There is some carrying capacity, which is finite, of the Earth's biosphere for human technological civilization. We don't know what the carrying capacity is. Perhaps it's a number greater than the 7 billion that we have today. Perhaps it's a number much smaller, and we're already past the point of sustainability in the biosphere. We don't know, but we do know that at some point there will be a limit. The only way to break out of that limit, we believe, is to go through what we call 3 gates. And they're all important. They're all essential. We have to get through all 3. The first is to dramatically reduce the cost of getting into space and moving around in space. And you see a lot of work by multiple companies in that regard today. The second is to learn how to use the resources that we find in space, because fundamentally they're infinite. For practical purposes in the solar system, those resources are not infinite, but compared to today's technological civilization capacity, they're effectively infinite. So when we learn to use the location and energetic and material resources in space for the benefit of humanity, that will enable us to break out of the constraints of the Earth's biosphere and then protect the biosphere in a way better than we're able to do today. The third gate, though, is equally important, and that is to continue inspiring future generations, because this project will become the most elaborate program in human history as we expand, and the rate of progress depends on people believing what can be done and committing themselves to it. So this is like building a cathedral where you lay out the plan and set the foundation stones, and no person working on it really ever sees, except in his mind or her mind, what the completed cathedral will look like. That's left for future generations. So it requires inspiring them, as well as learning how to use resources after we learn how to get into space and move around much more cost effectively. So this starts to explain why we're not there yet, why we don't have cities on Mars and we don't have hotels in Earth orbit, because we are still struggling to get through the very first gate, let alone the others. I've developed a model back in 2010 that I call the four futures, because at the time, working for the American Space Agency, it dawned on me that everything that the agency is all about is focused on exploring. And yet I think there are these other potential futures and objectives of our space program, and they drive us in different directions in terms of technology investments, systems we would develop, and operations that we would do. So it's important to understand which future we're aiming at if we're actually going to get there. We all know what exploring means. People have slightly different visions of its objectives and how important it is to be doing in space. But basically, exploring means to go someplace where that you've never seen before and learn what's there, study what's there, report back, and therefore, to succeed at exploring, it requires going to new places, and it requires reaching out as far as possible. That's why the American agency, NASA, has for over 40 years been focused on trying to get humans to Mars. If you're exploring, you must be reaching out to the next horizon and learning what's there, and that sets the frontier of human endeavor. What we really want eventually is to expand, and that's very different from exploring. It's filling in behind the wave of exploration with settlement. Settlement means civilization. Civilization means families, community, including multiple generations, generations that are born, grow up, mature, live their lives, and pass on. That is what civilization's about. And so we're not expanding until we're establishing civilization in a new place. The advantage of expanding into space is that it leaves, I'd say, old bad behaviors of colonialism behind, because there are no native ecosystems, there are no native peoples. It's all unpopulated land and territory and resources and volume. And so the trouble, though, and the reason that we don't have cities on Mars and hotels in space is because it's too far a bridge to get from exploring to expanding. No amount of government-funded exploration will ever emplace the infrastructure required for human civilization to settle in space. The difference in cost is many orders of magnitude. So the Four Futures model says that there are two other sectors that actually are the bridge from exploring to expanding, and they're the two in the center: exploiting and experiencing. Exploiting means extracting new value from resources that are found in a particular location. And so in terms of space, it means learning to use the special locations in space, the material resources that we will find distributed in multiple, very distant locations in some cases, and the energetic resources, particularly solar power, which is essentially unlimited in near Earth space. The experience quadrant is about bringing people into space, people who pay to be there for the experience of being there. So this is not exploring. I use a cruise ship to illustrate this. This is what I call fake exploring. This is a kind of exploring that I've done. It's safe. I'm taken good care of, but I get to go to places that are frontier for me, places that have already been explored by others, but I can vicariously feel some adventure of exploration in a curated environment. And I pay to do that when I go on a cruise or on a vacation overseas. And so that the magic of these two other quadrants, exploit and experience, is that they access sources of capital outside the top line budget constraints of government funded space programs. And until we do that, space activity will never grow beyond the rate that we see today. NASA spends about $25 billion a year on space. All the other civil agencies around the world together spend about the same amount. So that's $50 billion a year on basically space exploration and space technology. It will take way more than that to settle space. And the only way we can make that happen is by reaching into sources of capital that are not simply government budgets. You do that through entrepreneurialism and capitalism in the exploit quadrant, and you do it through direct engagement with consumers in the experience quadrant. So this is how the four futures play together. What's really important is to understand that the kind of systems that you would develop if you wanted to boost the activity in the two center quadrants is very different from the kind of systems you need if you're going to explore. If I want 6 people on Mars 30 years from now, that takes a different set of spaceflight vehicles and rockets and life support technologies than if I want to have a resort hotel in Earth orbit for 100,000 people a year. So it's important to know where we're going, what future we're aiming at in order to know what we should be investing in. I want to say a little bit about exploring, though. I'm going to start there with the moon, because that's the topic of interest for space programs around the world. It's the first next place we will be exploring in earnest with multiple nations, and calibrate our sense of cost and time. So this is an image to scale of the Earth and the moon, the Earth-Moon system, which is really a two-planet system. So the moon is really very close, just 4 travel days away. It doesn't take much more time to get to the moon from Vienna than it does to get to Antarctica from Vienna. And the moon really is an 8th continent. It has as much land area, surface area as Africa. So, and it's extremely geologically diverse with dramatic landscapes, particularly in the polar regions and on the highland far side. And there is lots left to discover and understand about this planet, both scientifically for its role in telling us about the history of solar system evolution, but also as a planet itself and as a place to learn to operate. But it's really very close, just 4 days away. Yet, it's a very hard problem. So on the left, you see an image of the International Space Station, which is, I would argue, the most impressive, extensive, peacetime, multinational technological project in history. But yet, as impressive as it is, in an image like this, you can see fundamentally the space station is just a few things. One is a way to get up and back, which we used to call a shuttle. It provides the shuttle function and is today provided by capsules. It's a very large system to get power in and heat out, and most of what you see in this image is exactly that. Solar arrays for collecting power and radiators for rejecting heat. And then a tiny cluster, a little warren of pressurized modules in the center. The interior volume of all those modules put together in the space station is about equivalent to the internal volume of a 777. So a small amount of volume, a lot of power in and heat out, and a way to get up and down. But it took the combined efforts of 16 spacefaring nations 30 years to develop that, launch it, and now operate it and use it. Let's go to the moon and see how hard that is. Well, for the moon, you still need a way to get up and down, some kind of shuttle into space and back to the Earth's surface. You still need a way to get power in and heat out on the surface, and those things need to be designed for lunar conditions. You need a habitable environment for laboratories and habitats, a warren of pressurized systems, the lunar versions of those things, just like in space station. But in addition, we also need a very large vehicle to get from Earth orbit to lunar orbit. We need another very large vehicle to get down to the surface and back up. We need all the systems to operate on the surface, to drive around, to do construction, to dig things up, flatten areas, and build infrastructure. And then finally, we need the capability to learn to extract resources from lunar materials so that we're not always just bringing everything from Earth. So if it took 16 nations 30 years to do the thing on the left, how long do you think it'll take to do the thing on the right? The point here is that even with the emergence of private capital and other interests and more engagement by more nations around the world, this is not a trivial thing. It will not be fast and it will not be cheap. And we should not be under any illusions about how hard spaceflight is. So even though the moon's only 4 days away, hundreds of times closer than Mars is, it's a very daunting challenge to end up with even a very straightforward laboratory on the moon like what we have in Earth orbit today with the International Space Station. Okay, I'd like to pivot now from exploring to some of these other quadrants, because this, as I said, is the economic engine. This is where the resources will come from for faster progress in space. So here I'll pose the question, what if power came from the sky? If you ask the average non-technical person today where electricity comes from, they'll say it comes out of a hole in the wall. A more sophisticated answer is that it comes from a power plant, which may be near or far. The power is transmitted over high voltage transmission lines. The power plant may be powered by nuclear power or by coal, typically, or by natural gas in most cases. There could be a future in which power simply comes from space. And to the average person, that would be power coming from the sky. What the part the average person would see is an installation, several installations like this. The one you're looking at here is approximately a 1 gigawatt system. This is enough to replace one typical size nuclear power plant. What it is a receiving antenna, what's called a rectenna for microwaves. And there's a lot of infrastructure in space to transmit power into this and then convert it to electricity and put it into the grid. But all that spaceflight stuff is what we worry about in aerospace. And most of the time, the space solar power community wants to show you pictures of what a space-based power station looks like in space. I think this is the more relevant image for most people on Earth. You know, what it would look like in the landscape, the fact that you can do mixed use land use, you can do agriculture underneath the rectenna. It's just an array of diode antennas, which is really just wires that are strung up. And so a very simple system on the ground. However, putting all the infrastructure in space to make this happen is expensive and will take time and will take dedicated systems. The opportunity is there for today's society to develop space-based solar power. Most nations are not doing so, but we'll talk about briefly somebody who is. If you did bring power to the surface of the Earth from space, enough, say 20 terawatts, enough to replace the power we use for mobile power systems so that vehicles would then be electric, charged from charging stations, powered by the grid is powered from space, and to desalinate seawater for drinking water, clean drinking water for the populations of the tropics, to power agriculture and industry in a growing future in which the developing world attains first world living standards. That's a lot of electricity. But if you did it, you would be building an amount of power infrastructure in space that's about equivalent to the paved area of the US National Highway System. That's a lot, but it's not magic. It's just large-scale engineering, and it could be done. If you did it, say power stations in the geostationary orbit transmitting power to the surface of the Earth, this is what the geography of space would look like. This shows you in the blue dot the Earth, and to scale the geostationary ring around it, 36,000 miles above the surface of the Earth. And what it shows you is the population centers of Earth arrayed in longitude, projected up to the geostationary orbit. So what you would find is that the most interesting cultures become neighbors in this future in space. That's why I call it urban geography. So San Salvador and Chicago are neighbors in space. Jerusalem and Moscow are neighbors in space. Fukuoka and Vladivostok are neighbors in this power-rich future in space. So it's just an interesting way to think about how bringing our power from the sky could begin to change how we view other cultures on Earth and ourselves as an integrated planet. There is one nation which is investing in space solar power, and you see it here. I'd encourage you to read carefully the quotation at the top. The designer of the Long March 1 rocket, so years ago, predicted this, and I believe this prediction. I think this will happen. The world will panic when we run out of fossil fuels. And then what's really geopolitically important is the next sentence. We must acquire, you could read that broadly or narrowly, we must acquire space solar power technology before then, before the crisis, before the panic. And so China has a plan by mid-century to in place commercial scale, grid scale level space-based solar power from geostationary orbit. On behalf of humanity, I wish them well. I'll pivot now to another wilder use of space. Again, this is in the exploit quadrant. And ask the question, is it possible to use space to somehow geoengineer our way out of the climate crisis and global warming? So we think big in space, as you probably know. So here's the Earth in orbit around the sun. If you were to put a dust cloud between the Earth and the sun, you could reduce the amount of sunlight hitting Earth by a very small amount, far less than 1%. You would not notice it looking up in the sky, but the Earth would notice it. The climate would notice it. The poles would certainly notice it. So, and that could be an external way of quickly reversing the planetary warming that we're experiencing. Maybe it would work, maybe it wouldn't. It's just an idea. Well, how would you do a big dust cloud in space? You could orbit dust around an asteroid to keep it in one location. We know how to move asteroids. There was a program several years ago called the Asteroid Redirect Mission that, if it had gone to completion, would have relocated a small asteroid to Earth-Moon space. So, but we know how to do this with mass drivers, and there's a lot of invention required and a lot of engineering, again, a large-scale program. But one could move an asteroid to the Sun-Earth L1 location, so it's always between the Earth and the Sun, and orbit a dust cloud around it. Because that would be a rotating system, the inertial axis is fixed in space as the Earth goes around the sun in the course of its year. So at sometimes the shade would be edge on, and at other times it would be face on. This could be timed so that it's face on when the poles are facing the sun at the solstices, so that we have differential cooling preferentially in the polar regions, which is exactly what we need to quickly reverse geowarming. And then, because I'm about settling space, if you need a big, heavy object as the center of a rotational gravitating system, like shown in the lower left, well, another thing we need a lot of mass for is radiation shielding for a space colony. So why not build an O'Neill settlement that has a lot of regolith as shielding that becomes the gravitating center of the dust cloud, and then we can do settlement and saving the Earth all at once. Not going to dwell on this. It's just an example of how, when we think differently about space, including how to exploit the resources we find there, in this case, material and location, how we could affect the trajectory of human civilization on Earth in a very positive way. This is not what you'll hear from space agencies who want to put 6 people on Mars. Now I'd like to pivot to the other important bridge quadrant, which is the experience quadrant, and ask the question, what if hundreds of thousands of ordinary people were flying in space every year? How might that change our view of ourselves and each other and the world? We know that astronauts who fly in space experience what's called the overview effect, a term that was coined by Frank White many years ago, to refer to the kind of multi-factor shift that human perception goes through when flying in space. It's a result, Frank hypothesizes, of the exhilaration of the physical ride up and down, the novel sensation of being suspended in free fall, and the incomparable view of Earth from the outside. The effect is strongest for people who travel furthest away. So the Apollo astronauts reported much stronger overview effect than even people in orbit. But everyone who flies in space experiences this. So if hundreds of thousands of ordinary people started to experience this every year, wouldn't that start to change how we view our planet and each other? Well, this is one of the reasons that Blue Origin and our partners are working to develop what we call orbital reef. It's named orbital reef with respect for the nature of what a coral reef is on Earth, which is infrastructure that's built by multiple small units, organisms, and they build this infrastructure, which in turn is the foundation of a rich ecosystem of species. So the coral reefs are the most productive ecosystems in the ocean, and there's a reason for that. There's energy input and there's a lot of activity, and species have a number of different relationships with each other. That's what we want to happen in Earth orbit. So multiple businesses, multiple types of human spaceflight travelers, including explorers and settlers, people from all types of industries, sharing infrastructure in order to conduct their lives or execute their business in space. So this will be a commercially developed, owned, and operated space station to follow the International Space Station, take over its research functions, and then provide capability for a richer array of business and private users. So, Earth orbit is very close, just a few hundred kilometers above our heads. So the view really is the most special view in the solar system. And we think we can turn that view to advantage by having Earth-facing windows so that the up direction inside what I call the sky canopy is the blue Earth above us. And a variety of what you would call traditional space activities inside, research, utilization, laboratories, but also more novel applications for orbital living. I mentioned resort hotel earlier. You can imagine things like a timeshare condominium for 12 wealthy owners who each own 1/12 of the year of a facility and live in space for 1 month a year. There are people around the planet who have amazing homes. Part of the objective here is to give some people some amazing homes that are genuinely around the planet. And the idea is that by expanding and enriching the amount of activity in space, we will then start to more normalize space travel as the cost comes down, the amount of activity and diversity of activity goes up, and then that provides a commercial foundation for capabilities that we then need to use to develop further out places and even support agencies in doing exploration. So it's meant to be a mixed use business park in space that would operate just like a business park does on Earth. The developer and operator landlord essentially would provide the infrastructure functions that are common. The tenants would have their own individual businesses. So imagine in that linear core you saw, that's the commons, the main street, if you will. And then off to the sides are the tenant modules. So behind one hatch may be a research laboratory, behind another hatch may be a hotel, behind a third hatch may be a microgravity film studio or a sound stage, so to speak. And so these different functions can then be optimized in their own modules. The attached tenant modules can be simpler because all the space flight infrastructure is in the linear core. The linear core is made of repeated units, so we can have an assembly line instead of everything that we launch being a bespoke, expensive system. We can start to get into the routine that launch vehicle builders are in of building the same thing many, many times. And then that provides fundamentally an address in space, a zip code, if you will, in space for businesses to operate. In a business park on Earth, if I'm the landlord, it doesn't matter to me if an individual tenant's business idea fails, because that tenant will give up the lease, and then I'll lease that space to a new tenant who has a different business idea and a different business. If I'm the tenant, I want to be focused completely on living my dream, making my business work. I don't want to worry about keeping the lights on or making sure that the sewer system works properly. That's the landlord's job. So by separating these functional requirements into these two types of business entity, these two business models, I decompose the large challenge of a viable operating business into a proliferation of small business decisions, which in fact is how cities have happened. So if you ask yourself, what's the replacement cost of Manhattan? It's unaffordable. Nobody knows what the number is, and it's unaffordable. You can't replace Manhattan. Well, how did Manhattan get to be there in the first place? It's because over a period of 400 years, individual entrepreneurs and individual bureaucrats in the government, the administration of the city, made local decisions that enabled small investments a step at a time. 400 years later, you have this megalopolis, which is unbelievably valuable and in fact couldn't be replaced. So when people look at things in space and say, well, that, we can never afford to do that, of course not. But we will be able to afford it with incremental decisions by diverse actors if we architect the business and the system in such a way that individual decisions can occur. That's the model for orbital reef. What we think it does give us the opportunity to do also is a new type of space architecture. So rather than being in a space station, sort of like one of my engineers calls it, like living inside a VCR. And that's because what we see in space today are laboratories. All laboratories look like that, on Earth as well. But not every function in space is a laboratory. If there's a resort hotel or a condominium or a conference center, a negotiation center for major treaties, for example, a sound stage, all these things are different functions. Not one of them is a laboratory. So there's no need for it to look like we're used to space modules looking. We can make space environments look the way we all knew they should. When I was growing up, when you were growing up, and the way we'd like to envision our future in space, we can build that today. So right now, my team is developing these windows that you see in this image, the largest windows that will have flown in space, because for private passengers, tourists, and a lot of business travelers, the most precious view in the solar system is something that should be celebrated and enjoyed, and we need to make sure that that happens. So as we enter the commercial realm, developing real estate in space, commercial real estate in space, it becomes a very competitive game, right? We need our environment to be appealing so that broader sectors of the economy will choose to participate with all types of products, from media and entertainment to industrial operations that can only occur in space to make products that could only be made in space, then return to Earth, and so forth. I just note here, you've seen in the video, but a couple of different types of systems. So the core module we've talked about, the inflatable life module that our partner Sierra Space is developing, gives a variety of interior environments and feeling of spaciousness. A single person spacecraft is a very exciting alternative to a space-suited EVA, safer, faster, much less expensive. And this is how we envision conducting necessary operations outside, or providing a tourist-safe extravehicular experience. I know when I went on safari to Africa, an add-on that turned out to be the most special part of the safari was a balloon safari. So if we're offering tours, highly curated experiences in space, there could be add-ons like going EVA in a single person spacecraft controlled by the computer so you can't crash it or kill yourself. And that could be an enhancing experience for the tourist. And then, of course, a variety of research modules and utilization modules as well. With this infinite modular architecture, we can simply grow the complex and add tenant modules as the market demands. So we increment our way into that future. So these were some examples of how we can think about utilizing the exploit quadrant and the experience quadrant to build the financial bridge to get us from just exploring to eventually expanding into space. I'll just say a couple of things just because I know people are curious about Blue Origin. We tend to be a rather quiet company. This chart is a few weeks old. We're actually at 10,000 employees today, distributed in these major locations around the United States. Our production operations are in Seattle and Huntsville and Cape Canaveral. We currently have 4 businesses. We build rockets and engines, suborbital rocket, orbital rocket, and engines. And then my business is the one on the right. It's everything that's not an engine or a rocket. It's all the in-space stuff. So multiple engine product lines. We make all of our own engines, both boost engines and upper stage engines and deep space engines. The one on the right is the engine for my lunar landers, a 10,000-pound hydrogen oxygen engine. New Shepard, our suborbital system, has flown 6 missions with humans. So 9% of all women who've ever flown in space flew on New Shepard within the last 2 years. And so we are rapidly changing the demographics of spaceflight and broadening access. We also fly commercial payloads, and we'll return to flight this year with an expectation of, again, multiple flights per year. New Shepard has turned out to be a very steady business for us. But New Shepard is small. You see it on the left here at the bottom with a human standing next to it for scale. The entire New Shepard system can fit in just the payload fairing of New Glenn, which is our orbital rocket that we're building in Florida. First launch will be in 2024. And this is a very, very large rocket. It's almost as tall as the Saturn V. And you see there on the right, its lift capacity to LEO and also to GEO. The first stage is fully reusable. The upper stage is expendable. The fairing is recoverable. In my business unit, we focus on several product areas. Next generation space transportation means making for example, the upper stage of New Glenn fully reusable, so the entire stack can be reused. And we also have very large in-space reusable systems in development. Remember, I said you have to get from Earth orbit to lunar orbit to be able to do the moon, so it's important for those things to be reusable as well. Space mobility means uncrewed systems, that is space tugs, orbital maneuvering vehicles for operations throughout cislunar space, tugs in LEO, platforms in GEO, deployment of a variety of commercial, civil, and national security customers throughout cislunar space and routine operations. Space destinations is exactly what it sounds like it is. It's places to go. That's where most of my human spaceflight teams are, including the orbital reef team. Lunar permanence is the program that we are developing to not just get to the moon, but to operate there continuously for the reasons I showed you at the beginning with the 3 gates. So we called it lunar permanence on purpose to get the point across that for us, this is not just, landing and walking around and getting video. It's about actually doing things. Some of the things we'll do depend on our other focus areas on the right. I have a whole raft of technology development projects, including liquefaction and storage of hydrogen and oxygen in lunar conditions. And then our first acquisition was Honeybee Robotics earlier this year. Honeybee is part of my team now, and they're the world leader in industry in interacting with planet surfaces and building things that make things move in space. So with these ingredients together, we can lay in place the pieces of the puzzle to start building the bridge to the moon, enable exploration, and start opening that path for the other quadrants, exploit and experience. And with that, I think I'll end, and perhaps we have a little time maybe for questions.